You already discussed dark energy, and dark matter is another major puzzle in cosmology since it's supposed to make up the bulk, well, with dark energy, the bulk of our universe's mass, but we have no idea what it is. What is the current, well, I think that the current paradigm is that dark matter is some sort of particle. That's what the general received view is. So, I mean, I just had a discussion with an astrophysicist who told me if I cut my hands, I've probably got 10 particles of dark matter in there right now. But I understand that that's not how you think of dark matter. And if I'm correct, that dark matter might not actually be matter at all. Maybe you could, if I'm right, you could spell that out for me and explain just how entropic gravity would have us conceive of dark matter, or what we observe as dark matter.
So you're right that now people think that dark matter is some kind of particle, but what we actually observed is a deviation from the gravitational laws that we can then sort of fix by adding more matter. But there's another way, maybe, namely that the gravitational laws are slightly different. Now, dark matter and dark energy are different things. Dark energy has to do with the expansion of the universe. It's some kind of, well, energy that's evenly distributed over space, and it causes the universe to expand faster. Now, they usually thought about as two different things. What I want to propose, and actually I did propose in my paper on emergent gravity, namely that there's a connection between the dark energy and the amount of dark matter that seems to be there. So I want to explain this deviation from the Einstein theory in a different way by the fact that there is dark energy. Now, one way you can visualize this is that the universe also has an entropy, namely associated to its horizon that we have. We have a cosmological horizon because the universe expands. But the reason why it's there is that there's also dark energy. So I think, and this is what I proposed, is that this entropy is associated to this dark energy. So the dark energy is everywhere, and also this entropy, therefore, can be everywhere. And that actually, the presence of that entropy is what makes this universe different, for instance, from this negatively curved universe. And it also may change the laws of gravity because it basically creates an additional force. So when we have a galaxy in our universe, it's surrounded also by this entropy of the dark energy. And it's the additional, you can almost call it the pressure that's due to that dark energy that creates the additional force. I mean, I can say much more about it, but this is kind of the way you can visualize this, is that the additional entropy due to dark energy is actually responsible for the amount of extra force. And nicely, actually, it also explains also precisely where the deviations start appearing. Namely, what happens in galaxies is that initially the stars are rotating exactly with the speed that we might follow from Newtonian or Einstein's theory, but it's only at a certain distance, or better said, is at a certain gravitational acceleration where things start to deviate. And this is explained precisely by this connection with the dark energy. And so I find it rather compelling that dark energy and dark matter are now part of the same story. And so we don't assume that dark matter is some unknown particle, because that would not have taught us anything about dark energy. I think that the problem of dark energy and dark matter are really about the same aspect of our universe, and that they somehow are part of the same theory. But also indeed with also explaining what gravity is about. So gravity, dark energy, and dark matter somehow can be explained together in our cosmos in a way that they fit together.
So dark matter, as currently conceived as particles, is supposed to be they're supposed to be extremely heavy particles, and so the way that we might observe them is in a particle collider that can accelerate particles to very high energies and thus produce them. But of course, on your view, this isn't going to work because dark matter isn't particles. But what this makes me wonder then is how, on your theory, we come to observe or measure or detect what we think of now as dark matter and dark energy. Is it an experiment, or is it just further refinement of theory?
So when the theory is developed to the point that we can indeed predict what's going on in galaxies when, for instance, when they are colliding or whether they are moving. I mean, there are certain things that galaxies are doing where we can think about this dark matter particle and try to model it. But maybe we have now with if we have a new theory, we can make predictions about what happens. So I think the way we're gonna make falsifiable statements is also by comparing to observations, but it's observations of the gravitational dynamics of galaxies or larger objects. So I don't think that we have an Earth-based experiment that can find these particles if they're not there, first of all. But dark matter is not something that is associated to a particle, in my view, and it's something that has to do with the way that gravity works in situations where we have, very small accelerations. We have to really go very far out in our cosmos to see these effects, or in our galaxy. There may be predictions that are closer to home, but then I would say within our galaxy, not within our, say, solar system, and certainly not a tabletop or some detector that's going to find it. But it doesn't mean that the theory makes no predictions. It's more in the observations that we can do in these cosmological astrophysical settings.